2.1, example 11, says to sketch a graph of each of the following and then determine if the function is differentiable at the indicated point. All right, so very quickly before we do that, what does differentiable mean? A function is differentiable at a point if it's what? The microphone's right here, so you can say lots of picks it. Oh, it's continuous first. It has to be continuous, but then it has to be continuous how? Smoothly, right? So the graph has to be smoothly connected or smoothly continuous at a point. And if it's smoothly connected at a point, we know that the derivative there will exist. Because remember what it means to be differentiable really is that the slopes from either side are merging in towards each other on any side of a continuous function at x equals c. So it has to be connected, and they have to be smoothly connected. So for a function like this is an absolute value of x function on part A. You need to be able to sketch this very, very quickly by using transformation. So if you factor the 2 out on the inside, you can think of that as your absolute value of x graph, and the 2 on the inside would be what? A horizontal or a vertical dilation if it's on the inside? If it's on the inside, it should be a horizontal opposite of what it appears. So it's not twice as wide, it's twice as narrow. So that would be a horizontal compression by a factor of 2, which essentially makes the graph steeper. Or you could factor that 2 out, and I think I mentioned on Friday that if you ever factor a number out of an absolute value, it's going to become positive. So even if that had been a negative 2, we factored out on the inside, it becomes positive when you factor it out. That becomes now a vertical stretch by a factor of 2. And they would have the same effect, right? Squeezing something horizontally in this case is the same as making it stretch vertically. The plus 3, though, moves our graph to the what 3? To the left. And that's pretty critical because of what the graph looks like at its vertex. It's going to look like that. Now, the number out in front of the absolute values or in front of the x, if you take plus or minus that number, that becomes the slope of the absolute value function on either side of the vertex. And since we didn't flip this one vertically, we know that everywhere to the left of negative 3, the slope is what? Negative 2. And everywhere to the right of negative 3, the slope is positive 2. But what is f prime in negative 3? What is the value of the derivative there? It doesn't exist. It's equal to d and e. Because even though the graph is continuous at negative 3, the limit of the y values from left to right are equal to the function value. The slopes are not the same from either side, and it's real obvious here to see that negative 2 and positive 2 are not the same right there where they meet. There's not even an attempt for them to like merge into each other. So no negative number as you come into a point is going to equal a positive number. So that's why it's not differentiable. And we said that that's going to manifest on a graph. Excuse me. We want to have some visual cues where something is not differentiable. And the visual cue here is that this one you can call a sharp turn. Some people call it a corner. And I said on Friday that they belong to a larger class of sharp turns / corners called cusps. And that's a fun word to say. So anytime you say a cusp on a graph, it's a little point that you wouldn't want to touch. Notice I'm dangerously close to touching it, but I'm not going to touch it because then I'd need a Band-Aid, right? So any sharp point on a graph is going to be a place where the derivatives are not the same from either side, and the graph will not be differentiable there. So anytime it's an absolute value of x function, you want to answer the question by sketching the graph. Now here's the follow-up question. If f prime of 3 is d and e, what is f prime of negative 5? Negative 2. Good. And f prime of negative 55? Negative 2. And f prime of positive 5? Positive 2. And f prime of positive 55.55? 2. Good. So absolute value functions now, if you can sketch them, if you can identify where the vertex is, that's the only place where it's not going to be differentiable. But the slope on either side should be plus or minus whatever that coefficient of x is. All right, questions about A? Sharp turn, cusps, not smoothly connected there. Differentiable everywhere except at 0. Did we actually answer the question? We didn't quite answer it. Let's go ahead and make sure we answer the question. F of x is differentiable, and that's a long word, differentiable, for all x not equal to what? Negative 3. That's the quickest way to then answer the question. If it's differentiable everywhere else, just say it's differentiable everywhere except at this point. All right, letter B, we got the cube root of x. The cube root of x, that's the inverse operation of doing what to a number? If you take the cube root of a number and you're like, oops, I didn't mean to do that, how can you get your original number back? Cube it, right? So the cube root of x and x cubed are inverse functions of each other. And here's what the graph of x cubed looks like. I know you know what this graph looks like, right? This is everyone's favorite disco graph. It looks like that and like that. It has a horizontal tangent line at the origin. How do we, in general, get the graph of an inverse function from the graph of a function? Yes, good. We reflect it across the magical line y equals x. So if I draw that in there and I reflect it across that line, here's what it looks like. I'll use dark blue. It's going to come in like this. And then look like that. So that dark blue graph there is going to be the cube root of x, also known as x to the 1/3. Same thing. Those are symmetric across line y equals x. Okay, so now I'm going to get rid of the purple graph, just so we can, the purple graph, so it doesn't get in our way of our analysis. What is the domain of the cube root of x graph, just by looking at it? What's the domain? All real numbers, right? All real numbers. It's continuous where? Also all real numbers, right? The y values are connected everywhere. All right, so for what values of x is it differentiable? Well, just looking at it, does this one look to be smoothly connected everywhere? Yeah, it looks very smoothly connected everywhere. But it tells us to look at it at x equals 0. Now, the graph at x equals 0 certainly looks smooth, but if you start analyzing what the tangent lines are doing, put the little tangent line surfboard here in negative x land, it's going to be a really small positive slope. And as I go to the right, surfing the curve from underneath, my slopes are still positive, but they're getting bigger, right? Bigger and bigger and bigger. As I approach the origin, they're getting bigger and bigger until right there at x equals 0, what does my tangent line look like? It's a vertical tangent line. And after that, then it's positive and decreasing. So right there at x equals 0, even though the graph is smoothly connected, we have a vertical tangent line. And if the derivative ends up being the slope of that tangent line, what is the slope of a vertical line? dne, right? The slope of a vertical line is dne because it's some type of infinity. And in this case, we could tell if it's positive or negative infinity. What was it? Positive or negative? My slopes coming in from the left were positive, 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 bigger, and then I got the positive infinity. Now, it's really hard if you're just looking at a vertical line to tell if the slope is positive or negative infinity. You have to kind of look at where it's coming from on the left and right. Okay, so what would you then say about f prime of 0? Right. Even though it's smoothly connected, since the derivative at 0 is undefined, because it's a vertical tangent line with an infinite slope, now f of x is continuous everywhere except 0. So f of x, differentiable. F of x is differentiable for all x not equal to 0. So this is kind of like the one where you need to be really careful about, because normally we can look for a cusp. If it's not smoothly connected there, it's not going to be differentiable. And that's still the case. But here's one that is smoothly connected, but it's not differentiable for a completely different reason. The slope is a vertical line, which, of course, doesn't exist. And that would be very similar to if you looked at the fifth root of x. What would the graph of the fifth root of x look like? Well, very similar, right? It would be a little bit steeper and less steep in certain places. But any odd root is going to end up looking like that. Now, if you remember, what was true of the square root of x at x equals 0? We've already looked at that guy. We even found its derivative. Was it differentiable at 0? Remember the square root of x function? What happened to the slopes as we were approaching the origin from the right side? They went vertical again, right? Because the graph of the parabola had a horizontal tangent line there. This is the inverse. It has a vertical tangent line there. And horizontal and vertical lines interchange when you reflect across the line y equals x. So all those radical functions, you got to be careful. On all those radical functions, the value of x that makes a 0 under the radical could be some kind of cusp or a vertical tangent line where the derivative doesn't exist. All right, let's look at x to the 2/3. Anyone know what x to the 2/3 looks like? We're going to throw this into your new parent function catalog along with x to the 1/3. All x to the 2/3 is it's your x to the 1/3 graph squared, right? Because 1/3 squared is 2/3. And what happens to your y values when you square them? What happens to these y values when you square them? Are we going to have negative values anymore? No. And in general, if the y value is bigger than 1 and you square it, it's going to become bigger. So it's going to be a little bit steeper, essentially, and it's going to be positive. It should have y-axis symmetry. So it's going to look like this, and it's going to look like that. And I call this one, of course, the bird graph. The bird graph. And simply because when you were little, right, and you drew those seascapes, remember drawing all those seascapes? You never, ever drew a seascape, hopefully, without drawing a sun in the corner, right? Using the corner to kind of block the sun. That was always a good idea. But then the finishing touch was to put sunglasses on the sun, or at least I did, right? Because it's bright up there. So those are melt-proof sunglasses. He was always smiling because he was cool. Maybe you drew like a little pink fin shark coming out of the water. But of course, the finishing touch was the birds, right? And you do maybe 2 of them, right? Oh man, that's beautiful. There's your seascape. That's why I call it the bird graph. It's x to the 2/3. Now, is this graph continuous everywhere? Continuous? Yeah. Is it differentiable everywhere? No, I don't think so. Do you see a sharp turn or a cusp? Is it smoothly connected? No. Right there at x equals 0, you have a cusp. Okay, it's a sharp turn. So the function looks like it's smooth everywhere else. So we're going to say that f of x is differentiable. And I'm going to abbreviate differentiable like that, diffable. Which you could do that between now and Cinco de Mayo. You can abbreviate differentiable, diffable. But on Cinco de Mayo, the day of the AP exam, you write it all out. For all x not equal to 0. Now, did you see how I wrote the word for all? You're allowed to use that. That's an inverted capital A. You can use that. It's a mathematical symbol that means for all. Yeah, it saves a little bit of writing. You can write out the words for all. You can just use inverted capital A. F of x is differentiable for all x not equal to 0. Now, you could say that it's not differentiable for a couple of reasons, believe it or not. First of all, remember, to be differentiable, the slopes from the left and right have to be approaching the same number. And as you come in from the left, your slopes are what? Positive or negative? They're negative. And they're negative becoming increasingly negative. As you come in from the right, your slopes are positive, becoming increasingly positive. So at 0, if you have a negative number and a positive number coming in, is there a chance that they're going to be the same? That they're becoming more negative and more positive as they meet? No. So that's one reason. But the real reason in this case is that, in fact, they're not only approaching a negative big number, but it's going to be negative infinity as you approach from the left. It does go vertical at the origin, and it's approaching positive infinity from the right. And in either case, the slopes don't even exist. Okay, so these actually do go vertical. But not on all cusps are you going to have vertical. Like if you look at my little bird right here that I drew, this doesn't go to negative infinity from the left, nor does it go to positive infinity from the right. But it's still a cusp because the two slopes on either side are not the same. What about the tip of the shark? Do you think that graph would be continuous at the tip of the shark? Or is that a sharp turn? Sharp point, cusp. Right, would you want to touch that? No, especially if it was attached to a shark. What about my beautiful little blue waves, the crest of my waves? Are they going to be differentiable there? No, right? Because we got cusp, 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 cusp. Very good. So you got cusps all over that picture. You didn't know it, but you were preparing for calculus when you drew that back in the day. All right, so we've got sharp turns, we got cusps, we got corners, and we have vertical tangent lines. Let's look at this one here, 10 minus x, square root of. Is this standard transformation form? No. Let's review how to do that. Under the radical, we want the x term to be first. And then if the coefficient of x is not a 1, you must factor it out on the inside, so we get x minus 10. So very quickly, let's sketch that. The parent function was radical due to x. Yeah. And what does the negative in front of the x do to any graph? Flips it or reflects it across the y-axis, right? If your x's are interchanging, positive x, negative x, they interchange. That happens across the y-axis. So this guy opens up to the left, and of course the minus 10 moves him to the up or to the down, or to the left or to the right? To the right 10. So it looks like that. And remember, because it's a radical function, it comes out kind of vertically and looks like that. Is this function continuous for all x? No, this function is continuous. F is continuous for all x less than or equal to 10, right? Is it continuous at 10 at the right endpoint? Yeah, we said it was continuous at the right endpoint because the function value at 10 and the limit from the left of 10 are the same. Is it differentiable over the same interval? No. It's differentiable everywhere on this interval except at what? X equals 10. Because right there at 10, what type of tangent line do we have? A vertical tangent line. Good. So then we'll say F is differentiable. Y'all like that upside down A? For all x less than 10. And of course, does it even make sense to talk about differentiability anywhere to the right of 10? No, it does not. So vertical tangent lines, even though the graph is smoothly connected there, in fact, I don't even think we could say it's connected there because there's really nothing on the other side. But there is a vertical tangent line there. All right, and then the last one here, we have piecewise function. Everyone loves piecewise functions. Now, it says to analyze this at -1. Notice what's going on here at -1. To the left of -1, it's going to graph as a line with the slope of what? 2. And to the right of -1, it's going to graph as another line with the slope of 2. So on either side of -1, what are the slopes everywhere? 2. I guess for y'all, it'd be like this. Does 2 equal 2? Are the slopes going to be the same from both sides? Yes. So should it be differentiable there? Well, not necessarily. Dang, you're not taking my bait. Why? Why not? Yeah. Just because the slopes are the same on either side doesn't necessarily mean that it's going to be differential, right? Because it must first be what? Continuous. And then it has to be smoothly continuous. Okay. So there's going to be a real quick way to determine differentiability later on using the alternate form. I'm going to show you right now what the alternate form is going to look like. We're going to use the alternate form here. Let's go ahead and let's use the alternate form. This is why the alternate form is actually in existence. This is like the one we warmed up with today. The alternate form is the way to test analytically for differentiability. And we haven't done it yet because we've just been sketching the graphs. Here's what it tells us. We need to look at the limit as x approaches -1 from the left of f of x minus f of -1 all over x minus -1. That's the alternate form. Basically, we're looking to see what's happening to the slope of the secant lines as we approach from the left. And then we'll do the same thing on the right. The limit as x approaches -1 from the right-hand side, f of x minus f of -1 all over x minus -1. Now, what the alternate form does is it not only checks to see if the secant line slopes are converging into the same thing, and we already said that the slopes on either side are both 2, but it also checks for the continuity piece. And the reason it checks for continuity is because in both pieces, we're using the actual function value f of -1 in both pieces, and that ties the continuity together. Let's go ahead and set it up then. For the first one, on the left side of -1, I have to use the f of x. I have to use the function piece that's actually defined to the left of -1, which is what? To the left of -1, we're using 2x minus 1. And then minus, what is f of negative 1? Do we use the top piece or the bottom piece? Or the middle piece? There is no middle piece. Top piece or bottom piece? Top. And what do you get when you plug in a negative 1? Negative 3. Yeah, good. All over x plus 1. Okay, if I simplify that, into negative 1 from the left, I get 2x minus, that's going to be 3, that's going to be plus 2. Is that right? 3 minus 1 over x plus 1. Now, if I try to evaluate that by direct substitution, what do we get? Zero over 0. Well, that's not a problem. We know how to eradicate that, don't we? We factor out the 2. We get x plus 1 over x plus 1. And everyone's favorite part, right? They divide out, and we're left with 2. Now, notice what we just determined. We just determined that as the secant lines approach the tangent line from the left side of negative 1, the slopes are approaching 2. Did we already kind of know that? We said the line was 2x minus 1, which is the slope of 2 everywhere. So, yeah, it's reasonable to think that. Now, what if we get a 2 on the other side? Then by the alternate form, it should be differentiable, right? Well, let's see what we actually get. We know the slope of the line that leaves at x equals negative 1 is 2. Let's see if the alternate form catches it, if it is or isn't. So now we're approaching negative 1 from the right. Now from the right of negative 1 for the f of x, I got to use 2x plus 1, because that's the function that we're using to the right. But notice I still use f of negative 1, which is still negative 3. That stays the same, all over x plus 1. If I evaluate that, I get 2x, and I get 3 plus 1, which is plus 4, all over x plus 1. Never not first. How do we evaluate? Direct substitution here gives us 4 minus 2, which is 2 over 0. And what's 2 over 0? It's some type of infinity. So you could say since 2 does not equal dne, which is true, dne is some type of infinity and 2 is not, f of x is not differentiable at x equals negative 1. All right, so this is a really good example to kind of talk about a little bit more. If you were to just look at, again, the slopes, they were both lines, and they both had slopes of 2 from the left and right. Differentiability is more than just slopes being the same. It has to be continuous first, and then the slopes have to be the same. Now, if I asked you later on just to determine if this thing was differentiable at x equals negative 1, and you didn't want to do the alternate form, could you just check for continuity first? Let's see. If you plugged in your negative 1, you get negative 2 for the limit from the left. You get negative 3 as the limit from the left. It's also the function value. The limit from the right is negative 1. Does negative 3 equal negative 1? No. And since the function is not continuous there, it's not going to be differentiable. So that's another way to determine it's not differentiable. But notice that the alternate form catches it. It's more than just the slopes being the same, the y values are being the same. So that brings us to this theorem, VIT, the very important theorem. Here's what it says. If f is differentiable at x equals c, then it's continuous there as well. If a function is differentiable at a point, then it's continuous at a point. We can summarize that with this. D implies C. That's what the arrow means, implies. What do you think D stands for? Differentiable. Differentiability implies continuity. So we have another way to check for continuity now, right? Instead of checking the three-step definition, limit from the left equals the function value equals the limit from the right, we can now just check to see if the slope exists there, right? And if the slope exists at a point, it's also going to be continuous there. Now let's look at some of these statements that you had in geometry. This is called an if-then statement. If D, then C. If it's differentiable, then it's continuous. You had something called the inverse of a statement. Do you remember what the inverse was? What the inverse does is it keeps the if-then order the same. It just negates both of them. So if not D, then not C. So we can write that like this. If not D, then not C. That's what that little symbol in front means. It means not. Is that true? If a function is not differentiable, then it's not continuous. Is that true? No. Counterexample? Will any of these work? Will this one work? Yeah, there was a function that was not differentiable at 0, yet it was continuous. So this is not a true statement. You also had another statement called the converse, which basically kept the positive part, but it flipped the if-then. So it would be continuity implies differentiability. Is that true? If a function is continuous at a point, then it's differentiable? No, that's a prerequisite, but just because it's continuous doesn't mean it's differentiable. Counterexample, any one of these, right? There's a function that is continuous, but yet it's not differentiable. So in general, the converse of a statement is not true. But then there was another one. Do you remember what the next name was called? It was one last statement. And it combined the inverse and the converse. It was called the contrapositive. And what it does is it negates the converse. So it says if not C, then not D. And that basically says if a function is not continuous, then it's not differentiable. Is that true? Yes. And in general, for an if-then statement, if the statement is true, then the contrapositive will also be true. It's only in an if and only if statement where all four of them are true. Now, the contrapositive is super important because, as we've already kind of noticed, if continuity is a prerequisite for differentiability, then we can spot places that aren't differentiable more than just looking for a cusp, more than just looking for a vertical tangent, right? In fact, if it's not continuous, it's not going to be differentiable. So we could spot that very, very quickly. So here's, again, the contrapositive of a very important theorem. If you know a function is not continuous at a point, because either there's a hole there, or a jump there, or what are some other discontinuities? A hole, a jump, a vertical asymptote, or the other one that we don't see that often, this one, an oscillation discontinuity, then the function is not going to be differentiable there. That's a whole new class or category of places where the derivative will fail to exist. If it's not continuous, it's not differentiable. Okay, so as we saw in example 11, then it takes more than just the slopes being the same from either side. It has to be continuous first, and then the slopes have to be the same. So here's one last function that's very similar to what we did up here on example E. We have a parabola, x squared, to the left of 1, and we have a line with the slope of 2 to the right of 1. If you were riding your whatever bike, skateboard, down this little ramp right here, then as you left the end right here at x equals 1, you would be flying off with the slope of 2. That's the slope of the graph right there at 1. And the line that comes in from the other side, of course, also has a slope of 2. So even though the slopes are the same from either side of 1, the slopes are merging towards each other. Will it be continuous, or will it be differentiable there? Sorry. No, because they're not going to be continuous. So this one says to verify using the alternate form. I went ahead and did the alternate form up here on part E. So here's what I'm going to do. If I ask you to determine if this is differentiable or not, here's what you're going to do first. Let's just check for continuity, especially if you suspect it's not continuous. So let's go ahead and review the three-step definition of continuity. The limit as x approaches 1 from the left of f by direct substitution is 1, which happens to be f of 1. So two of the three things are there. The limit from the left equals the function value. What's the limit as x approaches 1 from the right-hand side? Well, plug in a 1 into here, and you get $2 minus 80 cents. That's $1.20. Is the function continuous there? No. So will it be differentiable? No. So here's how you would string that argument. This is the continuity argument. Since 1 does not equal 1.2, comma, f of x is not continuous at x equals 1, and therefore is not differentiable, which I'll abbreviate as diffable, at x equals 1. So if I ask you, like on a quiz or a test, to determine if a function is differentiable or not, you could always check for continuity first. It's a little bit faster. It's a little bit easier. And if it's not continuous there, with the right things labeled and the right justification, then you can say it's not differentiable. Now notice how I wrote it. I said since 1 doesn't equal 1.2, and again I know where those values are coming from, f of x is not. Could I have just skipped the continuity part and just said since 1 doesn't equal 1.2, f of x is not differentiable at x equals 1? No, because what I did up here is not a differentiability argument, is it? So this would be like stringing together two logical consequences. Okay, because 1 doesn't equal 1.2, the y values are not the same, therefore it's not continuous. That's one theorem. And then because it's not continuous, then by another theorem, it's not differentiable. So you kind of need to string your argument along like this. But this is a valid argument. It's a little bit faster than the alternate form. If you did the alternate form, like we did up here on example E, you would get a similar result down at the bottom. You would get either two numbers that were not equal to each other, or one of them not existing, or both, possibly. Okay, there's one last thing I want to talk about, and then we're going to finish the notes, so we'll be done with this section. One last form of the derivative, and you're not required to know it. I just want to bring it to your attention for a very particular reason. This one's called the symmetric form definition of the derivative, and it also gives you a numeric value. So here's what it does. I'm going to show you graphically what the symmetric one does. Let's look at just some function f of x. And let's say I'm interested in finding the slope of the tangent line right here. Right there, at x equals c. I want to know what the slope of the purple line is. What we've been doing is we've been choosing the point of tangency c and one other point to the left or right. What the symmetric form does is it chooses another point that is, again, h units away. So that would be c plus h. But instead of finding the slope now of the secant line between c and c plus h, which is what we did in our modified form, it chooses another point that is h units away on the other side. Call it c minus h. And it uses that point there. And it finds the slope of the secant line connecting those 2 points. All right, so it does f of c plus h minus f of c minus h all over the change in those x values. Now, if you were just going to do one calculation as an approximation, notice the slope of the red line might be a pretty decent approximation of the slope of the purple line just because they have that parallel look going on in this particular case. But what should happen at the end is the same thing should result. Instead of keeping this point fixed and having that second point slide towards, now what happens as h goes to 0? What happens to both of these points as h goes to 0? They both converge towards the point in question. And so the secant slopes will still converge to the tangent slope. They're just doing it equally from both sides. So what it would look like is this. F prime of c is the limit as h goes to 0, and there it is. F of c plus h minus f of c minus h, and you end up with 2h in the bottom. And it gives you the same answer. Now, why do I bring this to your attention? Well, it's nice to always just have other options, but this is how your calculator is programmed to do it. Okay, your calculator can find numeric derivatives for you, and we're going to be letting it do that later on in the year. But you have to realize that your calculator doesn't have a brain like you do, and it is limited by its program. So let's look at this on the calculator. Using your calculator, if f of x is equal to the absolute value of x, we want to find the following. Okay, we want to find f prime of 2. So if you want to play along, this will be great. We're going to be using our calculator on and off throughout the year. One of the things that I would recommend doing is if you're going to be using your calculator with a particular function, especially later on when they get pretty big and ugly, go ahead and type it into Y1. So I'm going to go ahead and hit math number 1. That's how you get to the absolute value. Or you can hit alpha F2 or alpha window, and I think you got your shortcuts there. It's number 1. Okay, so once I have it in Y1, I want to find the derivative of my function at 2. If you have the new math print, here's all you have to do. If you click math and you scroll down to number 8, look, number 8 says nth derivative. You can either scroll down and hit enter, or you can just type 8. Now I'm in math print, so it shows up in Leibniz form. You can also get there by going alpha, I believe, alpha F2, alpha window again, And there it is on number 3. So there's 2 shortcuts to get there. Now here's how you would type it in. You read this as the derivative with respect to x. That's the verb. The derivative with respect to x. That's your independent variable of your function. So right here you can either put the absolute value of x, or you can recall it from y1, which is alpha trace. This is nice if the function was kind of nasty and you didn't want to type it in multiple times. And now this says evaluated at. This vertical line is the evaluation bar or the when bar. So this says take the derivative of the function with respect to x, Leibniz notation, evaluated at x equals, and we wanted what number? F prime of 2. Now before I hit enter, let's see what we anticipate the answer to be. The absolute value of x function looks like this, right? And 2 is right here. So what should the slope of the graph be right there at 2? Well, if the function is the absolute value of x, what's the slope everywhere to the right of 0? 1. And the slope everywhere to the left is -1. So this should be 1. Let's see if the calculator knows it. When I hit enter, it tells me 1. Okay, way to go, calculator. Let's try another one. I can hit second enter, which recalls it. And I can just come here and change the 2. Let's change it to 200. What's nice about doing it from the home screen is you don't have to have your calculator graphed to any particular window. What should the calculator give us? 1. Because that's the slope everywhere to the right of 0. Let's pick a number to the left of 0. Like what? -0.001? What should the slope be there? Everywhere to the left of 0, the slope should be what? -1. You think the calculator knows it? Hey, way to go, calculator. All right, what do we then think the calculator is going to give us at f prime of 0? What do we know about the derivative at 0? It should be what? It does not exist, right. The slope at 0 on the absolute value of x does not exist because there's a sharp turn there. -1 from the left on the slope doesn't equal +1 on the right. Let's see what the calculator thinks the derivative is at 0. Dun, dun, dun. You know, we've tried it out. We verified it with some numbers. We have now learned to trust our calculator, right? It's shown that it can do the work. So now we lean on it when we need it, and we get 0. So apparently the derivative of the absolute value of x at 0 is 0. So if this were a test question and I use my calculator, I'll do that, and I'll turn it in. And what do I put next to there? I put an X, and then I put a sad face, and then I put you. Well, I'll probably do it like this. You are smarter than your calculator. Is that how y'all would text it? That's using, yeah, that's 2 different yours, right? Would that be appropriate to text you are for 2 different yours? For you are and your? Is that how it works? I'm not that good. Why is it, why, what's wrong? What's wrong with that? Why do you think the calculator gave us 0? What do we know the answer to be? D and E. Does 0 exist? Yeah, very much so. So why does the calculator think that the answer is 0 when it's really D and E? Come on, you could talk bad about your calculator. It's an inanimate object. It doesn't have feelings. You want to call it stupid? It's stupid. Okay, yeah. It's programmed that way, actually, right? Do you see why it gives you 0? Anyone want to explain why? Knowing that it's programmed to give you the symmetric difference quotient, why would it give you 0? Well, if we're trying to figure it out at 0, it would pick a value h units away this way and h units away that way. And because it has y-axis symmetry, what's the slope of that line? 0. And then it knows that that's not the way to do it, so it'll pick values that are even closer, but symmetric on either side, and it'll find the slope of that. What's the slope of that line? 0. And it's not an idiot. It may be stupid, but it's not an idiot. So they don't choose points that are even closer symmetrically on either side. What's happening to those secant slopes as those 2 points converge? It's 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And so the calculator is then like, man, well, if I get zeros everywhere as I approach 0, then it's reasonable to assume that the slope there is 0, but it's not. So, you want to trust your calculator 100%? No. Would you take your calculator back to Walmart or wherever you got it with the receipt and then show them at the customer service, look, it gave me 0 here for the derivative of the absolute value of x at 0. I need my money back. You think that's a legitimate return claim? Not that it matters over there. They might just say, well, go get another one, right? And it does the same thing and you bring it back. That would be, don't do that. Don't do that. Okay, so again, we'll be using our calculator quite a bit this year, but who's the thinking partner in that relationship? We are. We are. All right, that's it. That's the end of that.